Today we're going to look at a technique of integration called integration by substitution. And it has its roots in uh, the chain rule. In fact, many questions that we're going to be able to do, you don't have to use the technique of substitution. You can use what I call undoing the chain rule. So here's how it works. So notice that if we take the derivative with respect to x of sine of the quantity 3x minus 5, we get cosine of the quantity 3x minus 5 times 3, right? And since derivatives and integrals are, I'm going to put air quotes around this, inverses, they're not really, inverse functions of one another, but they undo one another. The integral of 3 times cosine of 3x minus 5 dx would be sine of 3x minus 5. Notice the 3 goes away, right, when you take the antiderivative, because the 3 was born from the chain rule. And so when we take the antiderivative, that 3 goes away. So this gives you the general rule. If g is differentiable, and capital F is an antiderivative of little f, then the integral of f of g of x times g prime of x. So notice that's the form of the chain rule, right? We've got this function with an inside part times the derivative of the inside part. All we need to do then is take the antiderivative of this outside part and leave the inside part alone, and the derivative of the inside part goes away. Sometimes what we'll do is we'll take the time to say that in order to simplify something that's ugly primarily, we'll use a variable, typically u. Some books even call it u substitution, although there's nothing special about the letter u. U is equal to g of x, and du is equal to g prime of x dx. We could rewrite this as f of u du and just take the antiderivative. It's less ugly to look at than this is. Okay, and that's the whole idea behind u substitution. So if we were to look at this problem, the integral of x squared plus 1 to the 5th times 2x dx, if we let our inside part be x squared plus 1, notice we have exactly the derivative out here. It's 2x. So we just take the antiderivative of the outside part. So the outside part is raising this to the 5th power. So we're going to add 1 to the power, multiply it by the reciprocal of the new power, leaving the inside part alone. Bada boom, bada bing. That's our answer. We could also have taken the time to do the u substitution. If we substitute, if u is equal to x squared plus 1, I'm going to write this down here. If u is equal to x squared plus 1, then du would be the derivative 2x times dx. Some textbooks have you write du dx equals 2x and then multiply both sides by dx, but it's an extra step that you have to do on every single problem. It's more than we want to do. So now our integral will be the integral of, notice I've got the x squared plus 1, that's u, raised to the 5th, and the 2x dx is all du. So by doing the u substitution, we have something that is easier to look at. It's like a really good facelift. It makes that person easier to look at. So now we just take the antiderivative. That would be 1/6 u to the 6th plus c. And then we would have to, what I call unsubstitute. We replaced x squared plus 1 with u, so now we need to replace any u's with x squared plus 1. So this would be 1/6 of x squared plus 1 to the 6th plus c. Before we go on to some other examples, let me point out the strengths and weaknesses of each of these. Okay, the strength of the u substitution is you end up with an integral that has a much simpler integrand than certainly this. The weakness is it takes a little bit longer because you have to go through the whole u substitution part. If you can see that you have a composite function and that you're multiplying times the derivative of the inner part of the composite function, you can simply undo the chain rule and it's faster. Okay? On the AP exam, it used to be that although they said u substitution was something that you had to teach, there were no problems that you couldn't do without just undoing the chain rule. That is no longer true. There will be some where you have to be able to do u substitution. I'll point some of those out. I don't know if there are any on today's examples. I think there may be some on Monday's examples. So, let's take a look at these. For these, what we'll do is we'll look at, all right, let's do a u substitution, and then let's also do it by just undoing the chain rule. Again, you'll find that doing it by a u substitution takes a little bit longer. Undoing the chain rule is a little bit faster, but it's a little uglier. So it's going to be your choice on a lot of problems. So, how do I know that I'm likely to use a u substitution or undo the chain rule? I've got to have a composite function, and I do, multiplied by something that is related to the derivative of the inside part. So if I was doing a u substitution, I would let u be equal to the inside part, x squared plus 1. Then du would be the derivative of that times dx, so that would be 2x dx. Which is exactly what I have here. So I have the integral of sine of u times du. What is the integral of sine? Or the antiderivative of sine?
Negative cosine.
Negative cosine, exactly. So that would be negative cosine of u plus a constant, and then we back substitute, unsubstitute. So this would be negative cosine of x squared plus 1 plus c. For one like this, I personally wouldn't use u substitution at all because it's exactly in the form of the chain rule. I've got a composite function times the derivative of the inside part. All I need to do is take the antiderivative of the outside part. The antiderivative of sine is negative cosine. The 2x goes away because it was born from the chain rule, so when you undo the chain rule, it goes back away, and I'm right at the answer. Okay? So for that one, I wouldn't have done a u substitution. Are you welcome to do it? Absolutely. Let's take a look at this next one. This time we're going to have to do a little bit of rewriting in order to kind of see that u substitution may be helpful to me. This is the integral of, I'm going to rewrite the square root as the sine of x plus 6 to the 1/2 power times cosine of x dx. Let's go ahead and do the u substitution. Notice that the derivative of the inside part is exactly what we have on the outside. So that's nice. And we'll talk about what to do if it's not quite the same and you still want to undo the chain rule. So u is equal to sine of x plus 6. Du will be the derivative of that times dx, so that's cosine of x dx. So we've got the integral of u to the 1/2 times du. We'll use the power rule for antiderivatives, add 1 to the power, multiply by the reciprocal. That'll be 2/3 u to the 3/2 plus c. And then replacing the u with what we said u was equal to, we'll have 2/3 of the quantity sine x plus 6 raised to the 3/2 power plus c. Again, I'll point out, you could have done this just by undoing the chain rule. Once you have it like this, if you recognize that the cosine of x is exactly the derivative of sine of x plus 6, we just need to worry about the outside part. So we're just taking the antiderivative of something to the 1/2 power, which would be 2/3 of that something raised to the 3/2 plus a constant. All right, let's take a look at this next one. I find, for me personally, it's almost always better if I write the composite part first and then have the other part, because it looks more like the chain rule. So this will be the integral of secant squared of x cubed minus 7 times x squared dx. This one's a little bit different because what is outside is not exactly the derivative of what's inside, but we can deal with that. Here's how we'll do it. And I have a good friend who teaches this. He does it a completely different way than I do, and it boggles my mind. So here's how I do it. If you watch like a YouTube video or something, you may see some people do it differently than this, okay? Just don't want you to get confused, because I know that sometimes you guys will, you're like, I need to see something else, and that's fine, but just realize sometimes people do it a different way. It's not wrong, it's just different. So du will be the derivative of that, 3x squared times dx. Here's how I deal with it. What I do is go, okay, I don't want 3x squared dx. I want x squared dx, right? So that it exactly matches what's out here. Well, I'm just going to divide both sides by 3. So 1/3 du is equal to x squared dx. So now, when I do the u substitution, I'll have the integral of secant squared of u multiplied by, I'm replacing the x squared dx with 1/3 du, and I usually don't write the 1/3 in the integrand. I go ahead and factor it out immediately. Makes my integrand a little cleaner. So now I just need to know, well, what is an antiderivative of secant squared? Exactly. So this would be 1/3 of the tangent of u plus c. So this is 1/3 tangent of x cubed minus 7 plus c. Now, what if you wanted to do this by undoing the chain rule? Can you do it? The answer is yes. if you wanted to undo the chain rule, what you have to do is you have to make this into the derivative of the inside part. I'd really like that to be a 3x squared, right? How can I do that? Well, I would have to multiply this by 3, but that changes my answer. So I also need to multiply by 1/3, so that I'm really only multiplying by 1. So I could rewrite that as 1/3 of the integral of secant squared of x cubed minus 7 times 3x squared dx. Then you have a composite function where the derivative of the inside part is the outside part, or what you're multiplying by. So I just need to take the antiderivative of the inside part. So that'd be 1/3 of the tangent of x cubed minus 7. The 3x squared, the part that was born from the chain rule, goes away when I do the antiderivative. So plus c. Again, it's faster if you can do it without doing the u substitution. And all the ones we're going to look at today are ones where you don't have to use u substitution. I think it's on Monday that we look at ones where it's like, yeah, sometimes you don't have a choice. So let's take a look at this one. Again, I always start by rewriting it so that it's in a form that I like better. I'm going to rewrite that as 2x minus 1 to the 1/3 dx. I've got a composite function. I don't have anything outside, but the derivative of the 2x minus 1 doesn't have any variables in it. So that's going to be fine. If I do the u substitution, I'll let u be equal to 2x minus 1. Du will be then the derivative of that, 2 times dx. And I don't have a 2 dx, so I'll multiply both sides by a half. So half of du is equal to dx. I always want to say half of duh, because it looks like that. So now I'll have the integral of u to the 1/3 times 1/2 of du. So I'll keep the constant multiple, take the antiderivative of u to the 1/2, which is 3/4 u to the 4/3, all plus c. So that would be 3/8 of 2x minus 1 to the 4/3 power plus c. As is always true, you could, if you're really concerned with, I'm not sure that this is correct, take the derivative, make sure you do the chain rule. If you don't do the chain rule, you'll get a different answer, and you should get the original integrand. Again, if we wanted to do this without u substitution, we need what's outside the composite function to be the derivative of the inside part. So I really want that to be 2 times dx. All right. Well, I can accomplish that by multiplying by 2 and then compensate for that by multiplying by 1/2. So now it becomes exactly like what we did down here. It's 1/2 times 4/3 of 2x minus 1 to the 3/4. This should be 3/4. The other one's 4/3. Plus c, and we get exactly the same thing, 6/8 of 2x minus 1 to the 4/3 plus c. All right, One last example. Here we have a doubly composite function, which is fine because we have a composite function multiplied times it. Again, I spend time rewriting things. I would rewrite this as sine of 5x raised to the third power times cosine of 5x dx. So we have a composite function multiplied by a function that is at least close to the derivative of the inside function. It's not quite in this case. If we let u be equal to sine of 5x, then du would be cosine of 5x, but because of the chain rule, times 5 dx. That's not quite what I have in my integral currently, so then I'll multiply both sides by 1/5 and get 1/5 du is equal to cosine of 5x dx. So now our integral is u to the third times 1/5 du. And we'll just take the antiderivative. So I've got 1/5 times 1/4 of u to the fourth plus a constant. So that's 1/20 of the sine of 5x raised to the fourth plus c. Again, you could, I'm not going to write it out this time, but you could avoid all that by going, okay, I need this to be the derivative of what's inside. As long as you're only multiplying or dividing by a constant, you can do this. If you start trying to multiply and divide by a variable, that's not going to go so well, mostly because you can't factor it out. You can't factor out a variable of the integral. You can factor a constant out of the integral, but not a variable. So I would make this 5, and then I'd have to multiply by 1/5, and I end up with this same thing. I think you can see that pretty well. Okay, any questions about that? All right.